Beneath the quiet Swedish countryside 40 meters underground lies an unexpected and almost surreal sight. Deep, crystal-clear pools, illuminated by an eerie blue glow. Suspended in these waters are long metal canisters containing one of the most challenging materials human industry has ever produced: spent nuclear fuel. It is a place of profound contradiction, both highly dangerous and meticulously safe. This is the interim solution. But the question that has haunted the nuclear industry for decades is, what comes next? How does a society safeguard a material that remains hazardous for a period longer than all of recorded human history? Sweden has embarked on an unprecedented project to answer that question, aiming to build a tomb designed to last for 100,000 years. The intractable problem of eternity. The challenge of nuclear waste isn't its volume, but its longevity. As one expert explains, used nuclear fuel is so radioactive that it takes about 1,000 years for its radioactivity to diminish to just 10% of its original level. For it to fully decay requires a timescale on the order of 100,000 years. To put that in perspective, the Roman Empire lasted about 500 years. The last ice age ended roughly 10,000 years ago. Our institutions, our languages, and our very civilizations are ephemeral compared to the relentless half-lives of these radioactive elements. This creates a unique engineering and ethical dilemma. We cannot rely on administrative control over such vast stretches of time. The solution must be passive, and it must be geological. The Swedish answer: a journey. Deep underground. Sweden's response is a monumental project in deep geological disposal, a plan decades in the making. Managed by the Swedish Nuclear Fuel and Waste Management Company, SKB, the solution involves sealing the spent fuel forever within ancient bedrock. The process is a masterclass in long-term planning and technical innovation. The journey of the fuel is a carefully choreographed one. After cooling for about a year in reactor pools, it is shipped to a central interim storage facility called CLAB, located near Oskarshamn. Here, it is stored underwater in an underground hall for several more decades, waiting for its final journey. The heart of the permanent solution, however, lies further north in Forsmark. At this coastal site, engineers are constructing a vast underground labyrinth, tunneling 500 meters down into rock that is 1.9 billion years old. The encapsulation method, known as the KBS-3 concept, is a system of multiple redundant barriers designed to isolate the waste from the environment. The copper canister. Each canister has a thick steel inner core for strength and a 5-centimeter thick outer shell of pure, corrosion-resistant copper. It is designed to hold the used fuel for millennia. The bentonite buffer. The copper canister is placed in a borehole in the repository tunnel and surrounded by bentonite clay. This clay expands when wet, creating a tight, self-sealing buffer that is highly effective at blocking the movement of water and any potential radioactive particles. The bedrock. The final barrier is the stable, ancient rock itself, which has remained largely undisturbed for eons. This multi-barrier system is the result of over 40 years of research and testing, much of it conducted at the ASPA Hard Rock Laboratory, a subterranean research facility built specifically to simulate and accelerate the conditions of a real repository. The facility's director once explained that they intentionally chose a wet location for the lab to pressure test their materials and methods, ensuring they could withstand the environment's challenges. Weighing the future. Promise and peril. Sweden's path is groundbreaking, but it is not without its critics and challenges. The upside. A model for the world. The project has garnered significant international praise. An International Atomic Energy Agency (IAEA) review mission commended Sweden's comprehensive, robust, and well-functioning system, specifically highlighting the development of the KBS-3 concept as a good practice. For a country where nuclear power provides about 30% of electricity, and with plans to build new reactors, solving the waste issue is crucial for public trust and political legitimacy. It transforms nuclear power from a problem for future generations into a managed, closed-loop system, bolstering its credibility as a low-carbon energy source. The downside. technical and social hurdles. Despite the progress, significant concerns remain. Some scientists and environmental groups question the long-term integrity of the copper canisters, pointing to theoretical risks of corrosion over tens of thousands of years. Non-governmental organizations have filed legal appeals demanding more rigorous checks on this potential vulnerability. Furthermore, critics like Dr. Paul Dorfman of the Nuclear Consulting Group argue that deep geological disposal remains a concept, not a reality, with unresolved scientific uncertainties about how the materials will behave over such immense timescales. He suggests that the political drive for new nuclear power is using geological disposal as a fig leaf to make the technology appear more environmentally palatable. A legacy cast in copper and clay. The Forcemark repository is more than a construction project. It is a statement about intergenerational responsibility. It represents a fundamental shift from temporary storage to a permanent, passive solution. While Finland is the only other country to have approved a similar facility, Sweden's systematic, transparent, and scientifically driven process has made it a global benchmark. The project's success hinges not just on engineering, but also on a long-term commitment to social engagement. SKB has spent decades building consensus, with efforts ranging from public tours of its underground lab to extensive school programs. This painstaking work has yielded significant local support. In one 2010 poll, 81% of residents in the host municipality supported the facility. The tunnels at Forcemark are scheduled to begin receiving their silent, radioactive cargo in the 2030s, with the entire facility expected to be filled and sealed by the 2080s. Once the last tunnel is backfilled and closed, there will be no need for active maintenance. The site will be marked, not with grandiose monuments, but in a way intended to warn future civilizations away, a silent guardian for the next 100,000 years. In the end, Sweden's solution is a profound attempt to bridge the chasm between human time and geological time, entrusting our most persistent industrial legacy to the enduring stability of the Earth itself.